Welcome to the deep dive. Today we're tackling a really big question,
A huge one.
maybe one of the biggest of the century. Is a 100% renewable global electricity grid actually feasible? And, what's the sticker price for that future?
It's the ultimate challenge, right? Both from an engineering and, well, an economic perspective.
For sure.
And for this deep dive, we're really leaning on just one foundational piece of research. It's a paper titled Global Energy Storage Demand for a 100% Renewable Electricity Supply.
Right, and the first thing you'll notice if you look it up is the publication date. It's from 2014, so it is an older paper.
Yeah, and that context is everything. You really have to understand what they were trying to do here.
This wasn't a snapshot of 2014.
No, not at all. It was designed as what's called an overnight study. So they were looking ahead, sort of investigating the principles for the year 2030.
And using cost projections from 2020 to do it.
Exactly. The question was, if we had to achieve 100% renewables globally, how would we build that system and what would it cost?
So it's a theoretical stress test. And the main goal of this study was to figure out how much storage you'd need, and from there, the final price tag, right? The levelized cost of electricity, or LCOE.
That's the one. Basically, the all-in cost to build and run the power plants over their lifetime.
And their big conclusion,
Yeah.
let's just put it right up front, it was actually pretty optimistic.
Incredibly optimistic, yeah. This study basically demonstrated that a global climate-neutral electricity supply is, well, it's entirely feasible and at what they called a decent cost.
Okay, so what was that cost? Let's get the magic number out there.
The global average LCOE for their cost-optimized, fully decentralized system came out to 142 euros per megawatt hour.
142 EUR MWH. Okay, so that's our baseline.
That's the number we're working with.
And that is a fascinating finding, especially when you understand just how difficult they made the modeling for themselves.
Oh, absolutely.
Let's dig into that methodology. How granular did they really get?
The modeling was, for its time, extremely rigorous. They ran a detailed computer simulation that had to match the hourly electric load demand.
For every country.
For over 160 countries. I mean, think about that. They had to make sure the lights stayed on in the model for every region, every single hour of the year.
That sounds like a huge challenge, just filling the gaps when the sun isn't shining or the wind stops. So what energy resources were they allowed to use?
And they were really strict about it. The study confined itself to only 3 volatile sources.
Ubiquitous ones.
Right. Photovoltaic, so, standard solar panels, onshore wind, and concentrated solar power, CSP.
And here's the critical constraint that really defines the whole project.
Yeah.
It was modeled as highly decentralized.
Yes. They assumed you had local grids, but you couldn't really share power over long distances. They intentionally neglected any energy exchange between regions if the transmission lines were longer than 100 kilometers.
So every region was basically an energy island.
Exactly. They had to be self-sufficient every hour. And that gets to the real point of the study. And that 142 euro figure, their goal wasn't to find the cheapest solution.
No, it was the opposite. It was to find the most expensive, feasible one, right? To set an upper limit.
Precisely. And to make sure they established that upper cost limit, this study intentionally excluded some of the cheapest and most reliable renewables we have.
Like what?
Large-scale hydropower, bioenergy, geothermal power. All of it was just left out of the analysis.
So the logic is, if you can make a 100% renewable grid work for 142 euros under these, frankly, ridiculously difficult conditions,
Then the actual real-world cost, which would include things like cheap hydro and long-haul transmission, should be significantly lower.
that's the real optimistic takeaway here. That 142 is the ceiling, not the floor.
That's right.
Okay, so if you're relying only on volatile solar and wind and you can't move power very far, you're going to need massive amounts of storage.
A huge amount. Their model showed 35% of all global electricity demand had to be supplied by storage.
So what were the options? What did they include?
They used 3 major pillars. First, standard batteries, mostly based on tech like NAS or lead acid. Second, thermal energy storage, or TES.
So storing heat in, like, giant tanks of molten salt.
Exactly. And then using that heat later to run a steam turbine. And finally, renewable power methane, RPM.
Which is the power-to-gas process.
Right, you're basically converting renewable electricity into a gas you can store and then burn later.
Now, this is where the findings get, I think, really counterintuitive, because when we talk about renewables today, the conversation is all about batteries. What did the cost-optimized mix actually look like in this study?
Well, you're right. It is surprising. Batteries actually played a relatively minor role in the system.
Minor.
Looking at the global annual energy output from all storage, batteries supplied only 6%.
6%. That's it. So what dominated?
Heat and gas dominated. TES, that thermal energy storage, provided the vast majority. We're talking 4,800 terawatt hours, which is a massive 67% of all stored energy. And RPM, the storable gas, provided the other 27%. You can see this clear split. TES is preferred for the short-term stuff, covering daily dips. But RPM is required everywhere for that long-term seasonal energy storage.
That makes perfect sense. Heat storage covers a few hours, maybe a day, but if you have a month of low wind, you need a fuel you can save for months. But why was TES so cost-effective? Why did it beat out batteries so completely in their model for short-term storage?
It all comes down to utilization. The secret is the steam turbine component. The model showed that the steam turbines were highly utilized. They averaged 3,760 full load hours a year.
So they were running almost half the year.
Almost half the year. And the reason is their versatility. The steam turbine wasn't just a one-trick pony. It had a triple function in this scenario.
Okay, so what were the three functions?
Well, it converts thermal energy directly from the solar collector field, for CSP. It converts the energy that was stored in the PES tanks, and crucially, it also converts thermal energy generated from burning the RPM.
So you're channeling heat from the power-to-gas supply back through the same turbine.
Exactly. Because that one component can handle three different inputs, its cost per unit of electricity just plummets, and that made TES the economic winner.
That's a great example of system optimization.
Yeah.
Okay, so moving from the global average of 142 EUR/MWH, how much did the LCOE actually vary from country to country?
The range was pretty significant. It went from a low of 80 euros per megawatt hour all the way up to a high of 203.
Who came in with the lowest cost?
That was Somalia at 80 EUR/MWH. And that was attributed to its, exceptional solar and wind resources.
And that's an incredible finding when you think about it.
It's even more striking when you note that, according to the data they had, the actual cost of electricity in Somalia at that time, mostly from diesel generators, was estimated at over 1,000 EUR/MWH.
So a shift to 100% renewables would mean an almost tenfold decrease in cost.
A massive decrease.
And which country was at the top of that range?
The highest cost was modeled for Bosnia-Herzegovina, topping out at 203 EUR/MWH. And the model said that was mainly due to poor wind and solar conditions in the regions analyzed.
Which brings us full circle back to that upper limit constraint we talked about.
It does.
That high cost for Bosnia-Herzegovina is almost certainly an overestimation because we know the country has huge untapped hydropower potential.
Estimated at over 6,000 megawatts, and that was completely excluded from this study.
So it perfectly validates their approach. If you exclude the cheap, reliable stuff like hydro, costs go up. It confirms the numbers really are a ceiling price.
It does, and the spatial distribution showed the same thing. You saw batteries favored in tropical regions with lots of PV, TES near the equator with high direct sun, and RPM needed everywhere for that seasonal backup, especially in windy places like southern Argentina or the North Sea.
So to wrap up the key takeaways of global energy storage demand for 100% renewable electricity supply.
Well, this study, it really confirms the economic feasibility of a 100% renewable global electric sector. Even with these severe constraints, no hydro, no long-haul transmission, the cost-optimal system gave them a baseline average of 142 EUR/MWH.
And it did it by relying primarily on highly utilized thermal and gas storage solutions, not just batteries.
That's right.
And, that leads to a final compelling thought for me, specifically about that power-to-gas process. RPM was the most costly and, I think, least efficient storage option they included. Yet the optimization proved it was an absolutely central, non-negotiable part of the system.
You had to have it for seasonal storage, especially once you got above 80% renewables. It was expensive, but required.
And this is the real significance, this study only asked RPM to match the electric load. But RPM is so versatile that renewable methane can be easily distributed and used in other energy sectors.
Oh, for sure. For heating homes or fueling heavy transport.
Exactly. So its total economic value to a completely carbon-neutral economy is likely far, far greater than its costly but necessary role in just the electricity sector alone suggests. And that's the kind of systemic integration we really need to be thinking about.